OK. All right. Thanks, Danny. So hello, everyone. I'm Yin Huai from Databricks. I'm a Spark committer and a Hive committer. So today, I'd like to talk about Catalyst, which is the optimizer in Apache Spark. So before I dive into Catalyst, so let's start with some background materials. Let's look at how we write code using RDD API. So let's say I have a SQL query, and I'd like to write a program to evaluate this SQL query. And this query is very simple. So I start with a inner drawing between two tables, T1 and T2, and I filter the result of the drawing using two predicates. And the first predicate is that the value of ID from T1 needs to be equal as the value of ID from T2. And the second predicate is that the value of ID from T2 needs to be greater than the result of 50 times 1,000. For the result of the filter, I select the value of T1.id, and finally, I count the number of values. So let's look at two versions of code using the RDD API. For the first version, I use a Cartesian function to calculate the drawing. And basically, the Cartesian will generate the Cartesian product using rows from both T1 and T2. And after the Cartesian, I applied the filters using two filter functions. And finally, I select the value of ID from T1 and calculate the count. OK, this is the first version. And this is the second version. So for the second version, instead of doing the drawing at the beginning, I apply a predicate, which is T2.id is greater than 50 times 1,000. And I apply the filter first on the T2. And after that, I use a drawing function to drawing T1 and T2. And this drawing function also will evaluate the condition, which is T1.id equals to T2.id. And finally, I get the result of ID from T1 and calculate the count. So these two versions of the program looks roughly have the same amount of code, but actually they have totally different performance. So I compare the performance of these two versions using Databricks Community Edition. And in my test, the T1 had 100,000 rows, and T2 had 10,000 rows. And here's the result. Basically, the first version took about 50 seconds. However, the second version only took 0.25 seconds. And here is a 200x difference. So what is the reason of that? And why is here showing 200x difference? So let's look at the code again. So the first version, we have Cartesian, and we apply filter. So basically, we generate the Cartesian product at first, no matter and without knowing what predicates we want to use. So basically, we generate tons of rows that will be filtered out by the filters. Actually, for the second solution, we apply the filter on T2 first, and also when we evaluate the drawing, we apply another predicate. So in this version, we're eliminating lots of unnecessary rows. So basically, this difference generates a totally different result. So when you write a program using RDD API, so basically your functions are black box. Your computation are opaque, and you have opaque data type. Basically, Spark knows nothing about your function, knows nothing about your data. And the programs built using RDD API have total control on how to execute every data operation, which means as a developer, I have to write efficient program to get good performance. This sounds pretty hard, because even as an experienced developer, for different kind of workloads, I often need to spend time and efforts to come with the good solution. So is there an easy way to write efficient programs? So the answer is actually yes. So the easiest way to write efficient programs is actually don't worry about it, and just get your program automatically optimized. So how to do that? So the first, you need to write a program using high-level programming interface, which means the programs are only used to describe what data operations are needed without specifying how to execute those. Fortunately, in Spark, you have SQL, you have a data frame, and you have a data set. So the next, once you have a program built using the high-level program interface, you need to get an optimizer that will automatically find out the most efficient version of your plan, of the query plan. And that can efficiently execute those data operations. And in Apache Spark, the catalyst is the optimizer. So let's look at how Catalyst works. At high level, Catalyst has an internal representation of a user's program, which is called a query plan. So the high-level program interface basically is a public API of building query plan. So once we have the initial version of the query plan, Catalyst will apply a different kind of transformation to convert the query plan to an optimized query plan. And finally, through Spark SQL's code generation mechanism, the optimized query plan will get translated into a DAG of RDDs, which are ready for execution. So at its core, the Catalyst defines abstraction of users' programs as tree and transformations from one tree to another tree. So now let me introduce these two concepts to help you understand how Catalyst works. First, let's look at the trees, which are the abstraction of a user's program. So for a program built using the high-level API, for example, this SQL query, so we need a new way to describe how to generate a new column from using the input columns. And the expressions are used for this purpose. So in this SQL query, you can find there are 5 expressions, like sum, like 1 plus 2 plus id.value, and also you can see there are 2 predicates. And in Catalyst, the columns are also represented by the attributes. And the attributes are also expressions. So basically, an attribute can represent a column of a data set. So in this case, like t1.id represents the column ID from table T1. Or the attributes can represent a column generated by a specific data operation. So in this case, you can see like V is representing the result of 1 plus 2 plus T1.value. So now we have expression to describe how we generate a new column using input columns. We also need a way to describe how we generate a new data sets using the input data sets. And a query plan are used for this purpose. So a query plan is used to describe a data operation like aggregate, join, and filter. And those operations will generate a new data set based on the input data set. And a query plan uses one or multiple expressions. So here is an example query plan. You can see that we have scan, join, filter, project, and aggregate. And those nodes corresponds to operation defined in the SQL query. And in Catalyst, there are 2 kinds of query plans. The first kind of query plan is a logical plan. The logical plan describes computation on data sets without defining how to conduct the computation. And every logical plan has a list of output, which are represented by the attributes. Like for example, in this case, like ID and V are 2 attributes representing output. And also, a logical plan has a property which is called constraints. A constraint represents a set of environments about the rows generated by this plan. So for example, in this case, we have a filter, and one of the environments is that for the output rows of this filter, the value of t2.id must be greater than the result of 50 times 1,000. OK, and now this is a logical plan. The logical plan does not define how we actually execute the data operation. So we need another abstraction to actually let Spark know how we evaluate operations, and which is a physical plan. And a physical plan is basically describe a computation on data set with a specific definition on how to conduct the computation. And a physical plan is executable. So here is an example. So you can see like for the drawing node, the name is not just a drawing, it's actually sort merge drawing, which means the sort merge drawing algorithm is a drawing algorithm for the drawing operation. OK, so now I have introduced the tree, which are the abstraction of a user's program. So let's look at transformations. How we transform a tree to another tree. So in Catalyst, there are two kinds of transformations. The first kind of transformations are used to transform a tree to another tree in the same type. So you can use this kind of transformation to transform an expression to another expression. You can transform a logical plan to another logical plan, and you can also transform a physical plan to another physical plan. And in Catalyst, there are two ways to implement this kind of transformation. The first one is a transform, and the second one is we call that rule executor. And the second kind of transformation is we transform a tree to another kind of tree. So in Catalyst, we use this kind of transformation to implement the conversion from logical plan to the physical plan. So let me introduce these two kind of transformations. So I will start with the transform. So the transform is a function associated with every tree and is used to implement a single rule. So let's say we have an expression tree like this. We have a 1 plus 2 plus t1 dot value, and you can see the expression tree at the bottom of this slide. And you probably notice that we have 1 plus 2, and this expression having two constant value as operand. You probably don't want to evaluate this expression over and over again for every input row, right? So instead of evaluating 1 plus 2 for every input row, so how about we just evaluate it once at the compilation time? So at the runtime, I don't need to bother about it. So we can use transform to implement a rule to evaluate the 1 plus 2 before the execution. And after this transformation, we got 3 plus t1 dot value. So let's see how transform is implemented. So transformation is basically defined as a partial function in Scala. So a partial function is basically a function that's defined for a subset of these possible arguments. So here is a very simple example. We have expression, we call it transform, and we provide a partial function to this transform. And you can see the case statement here determines if the partial function is defined for a given input. So in this case, so the transform is defined only to the add expression, and the children of the add expression need to be constant integer values. So now let's see how this rule will work with the expression tree we have. So the first, when we use this tree to transform, when we use this rule to transform the tree, we'll first visit the add operation at the top. And here we can see this rule will not be triggered because the right child of this add is not a constant value. It's actually an attribute from the table T1. So then we'll going down to the tree and find another add. And here we see, oh, we have a new another add expression, and we see, okay, we have two constant operands, and they are both integer. So this rule will be triggered, and we will convert this tree from 1 plus 2 plus t1 dot value to 3 plus t1 dot value. So it's pretty cool. We can use transform to convert your tree to another version of the tree. So how about, and oftentimes we want to combine different kind of rules together and make the change that cannot be done by a single rule. So let me show an example. So here we have a credit plan tree, and you probably notice that we have on top of the drawing we have the filter which contains two predicates. But here we don't know, but probably the drawing will generate lots of unnecessary rows, and those rows will be filtered out by the predicates in the filter. So how about we push down the filters? So we use a rule called predicate pushdown to push the filter. So one filter will be pushed into the drawing because it uses column from both tables. Another filter, T2.id, is greater than the time, the result of 50 times 1,000 will be pushed through the drawing because it only uses the column from T2. And if you recall the RDD program I mentioned at the beginning, so this essentially is the most important change from the solution 1 to solution 2, and that resulted in 200x speed up. Okay, so this is the new version after the first rule got triggered. And you look at the query plan tree again, you find, okay, there's some expression. Looks like they are using constant values. For example, you have 1 plus 2, and we also have 50 times 1,000. So how about we evaluate those at the compilation time instead of evaluate those at the runtime for every row? So now we trigger a constant floating rule that will evaluate 1 plus 2, and it will also evaluate 50 times 1,000. So after the constant floating, this is a query plan tree. And by looking at this tree, probably notice that we only use certain columns. Let's say for the table T1, we only use column ID and value. And for table T2, we only use the column ID. So it's better to specifically say we only want these columns. And so to help Spark understand, we don't need other columns and to avoid like unnecessary operations. So now we use a column pruning rule that specifically add project on top of the scan node that will give us the only needed columns. So this is pretty cool. Out of these three, we put all of these 3 rules together, and we make a change of the query plan tree that cannot be done by a single rule. So how this transformation is implemented. So in Catalyst, a rule executor is basically used to transform a tree to another tree by applying many rules defined in batches. For every batch, we can have multiple rules. And every single rule is implemented based on the transform I introduced before. And there are 2 ways to apply rules in a batch. So the first, we can apply those rules over and over again until the tree does not change. And we call this approach fix a point. For the second approach, you can simply apply rules defined in a batch just once and then apply them sequentially. So we call that like once. All right, so now I have introduced how we transform a tree to another tree with the same type. So how about let's look at how we transform a tree to another kind of tree. Specifically, how Catalyst convert a logical plan to a physical plan. So in Catalyst, a logical plan is transformed to a physical plan by applying a set of strategies. And every strategy uses pattern matching to convert a tree to another kind of a tree. And here's an example. It's a very simple strategy called basic operators. So here, you can see there are 2 rules. The first rule is we convert a logical project operator to a physical project operator. And the second rule is we convert a logical filter operator to a physical filter operator. And whenever a strategy see any kind of a logical plan that it doesn't recognize, so the strategy will call the plan later, which will trigger other strategy to help us convert that part of the tree to that part of the logical plan to the physical plan. Okay, so now I have introduced the trees and the transformations in Catalyst. So let's look at how Catalyst exactly transforms a user program to an optimized version that is ready for execution. And this process is done through 3 steps, which are analysis, logical optimization, and physical planning. So for analysis, it's implemented by using the rule executor. There are a bunch of different kind of rules that will analyze your query. So it basically transforms an unresolved logical plan to a resolved logical plan. So here, the unresolved means that we don't know the data sets and the column, where the data set and the column are coming from, and we don't know the type of your column. So for the resolve, it means we get all of those information. We know where are our data sets, we know where are our columns, and we also know what the column types. So after the analysis, the next step is a logical optimization, which is also implemented using the rule executor. And it apply a bunch of optimization rule to convert the tree from a resolved logical plan to an optimized version. And finally, we need to convert the logical plan to the physical plan, which will be submitted to the Spark for execution. So we have physical planning, which is implemented using both strategies and the rule executor. It's basically transform a optimize the logical plan to a physical plan. So let me talk a little bit about the physical planning, because it's used both strategy and the rule executor. So basically, the Spark's planner is a 2-phase planner. So in the first phase, it's transformed the logical plan to the physical plan using the different kind of strategies. And after we got a physical plan tree, we will use rule executor to make the physical plan ready for execution. So in this phase, we basically do the following 3 things. The first, we will prepare scalar subqueries. And the second, we will try to ensure the requirements on input rows. Because for a physical plan, it may have requirement on how the input data need to be organized. So we use this step to make sure the input rows of a physical plan is organized in the required way. And finally, we will apply physical optimization. So here, let me use one example to help you understand what we do in the second phase. And the example I would choose, the ensure requirements on input rows. For a physical plan, for example, sort merge join, so it has requirements on how its input row need to be organized. So for sort merge join, we want to make sure the input rows are sorted based on the join condition. And let's say the join condition is t1.id equals to t2.id. So we want to have the t1 needs to be sorted by the value of the ID, and also t2 needs to be sorted by the value of ID. So when the t1 and t2 are not sorted, the Spark's planner will automatically insert the sort operator to sort the rows and make sure the output of the input of the sort merge join satisfy its requirements. So what about if the T1 has already been sorted? So because if it's already sorted, we don't need to add a sort again, because the sorting again is just like a waste of time, right? So the Spark's planner is smart enough to detect this kind of a case, and you'll avoid inserting the sort. So this will, if the T1 is already sorted, and this will be the part of the tree, and we only sort the rows coming from T2 side. All right, so I've introduced what is Catalyst and how it works. So let's put it in the context of Apache Spark and see how it is used by the other components in the Spark and how it is used by other projects in the Spark ecosystem. So let me show you the separate stack. So at the bottom of this stack, we have Spark Core and RDD API. And we have Spark SQL on top of the Spark Core. And we provide SQL, data frame, and dataset API to users. And Catalyst is essentially convert the user's high-level program to the physical to the version using RDD that can be executed efficiently. Although you can still use RDD API, but with the Spark 2.0, we expect most users will migrate to the high-level API, which are SQL, data frame, and dataset. And on top of the data frame and dataset, we also have other libraries built on top of them. Like, for example, ML pipeline, structured streaming, and graph frames. Because those are built on top of data frame dataset, so your program built on top of those libraries will also be automatically optimized by the Catalyst. OK, cool. So that's pretty much the end of my talk. So if you want to learn more, so let me show you where to start. To study Catalyst, the best reading material are the source file of the trees like expression and the transformation like analyzer, optimizer, and a planner. And you can also check out Praise pull request and to see how others are implementing the new feature or improvements using Catalyst. And finally, to quickly get hands-on experience, so I write some code using Catalyst. And here, let me show you 2 examples of a previous pull request. So the first one is we add a drawing rewarding in the optimizer, which is adding a new optimizer rule. And this code, this pull request is about 200 lines of change. For the rule itself, it's only 100 lines. So it's a very, very small patch. And with this new rule, certain workloads can run 100 times faster. So it's actually very powerful. We have a very small rule, and you can help us get a very good performance for certain workloads. OK, the second example is adding pivot table support in data frame API. So basically, this one add a rule in the analyzer to help Spark understand how to convert a pivot table operation to its internal representation, which is query plan. And the patch itself is about 250 lines of change, and the analyzer rule is about 150 lines. Still, it's a pretty small patch, and a very useful feature to data frame. So that's pretty much all about my talk. If you want to try out Spark and try out the new preview version of Apache Spark 2.0, check out Databricks, and you can sign up on the community edition, and you can start to run your program using Apache 2.0 preview. And you can also try different versions of Apache Spark and see how the optimizer got evolved. So that's pretty much all about my talk. And I have an office hour from 2:45 to 3:30. If you have any question, find me at that time.
So we have time for 1 or 2 questions, but as he noted, he's got office hours this afternoon, so you can also ask questions then. But if you want to try to toss in 1 or 2, by all means, please come to the mic in the center row and ask your question, please. Go ahead, second microphone.
Yeah, I had a quick question about reduce by key operations, and what does the physical plan of reduce by key look like? So you spoke a lot about sort merge join. I don't know if that's also used for reduce by key.
Yeah. So you're talking about the data set reduced by key, right?
Right.
OK. Yeah, the reduce by key is actually using the same physical operator as a normal group by aggregate. So you can.
Does it use a shuffled hash join like approach, or does it do some map size sorting as well?
It depends on how your data is organized. If your data is already grouped, then there's no need to shuffle the data. But if your data is not grouped in the right way, we will shuffle the data. And we do have partial aggregation. But so you can you can call explan to print out the plan, and you will see, and you can compare that with the regular group by and aggregation. It's pretty much the same. Yeah.
Actually, we're going to have to cut it short. So could you repeat your office hours today, please?
Oh, my office hour is from 2:45 to 3:30 at Expo Hall. So
perfect.
if you have any other questions, find me out there.
Awesome. Well, thanks very much, everybody.